And what we'll do is I'll end this and we'll go back and do 11.5. Okay. We finished pretty much 11.4 last time, right? Okay. That was as close as I've gotten to finishing an entire, everything that we needed to cover in one term. But that's because they had the classes way too long in the summer, which gave us time to do that.
You touched on, you talking about lines, planes, and the surface.
Right.
Space. You
Right.
touched on it.
Right. Okay.
I didn't get it. So.
Okay. Well, let's go back to that then, and I'll even turn on the projector. So you can see what I'm talking about, maybe. And we'll go from current slide. Oh! Let me turn on screencast. Oh, it's already on. Okay. Yeah. Yeah. I had forgotten to turn that one on. So we'll go from current slide. Finally, it'll come up, I think. Today was the first day all week I've been able to eat lunch. Okay. I crammed it down in those.
Yeah, I was saying, even with lesson, you took time, it should have lunch. I honestly most of that.
It's, I found that I could live without lunch this summer because of that Monday, Wednesday, and Friday, or Monday and Wednesday, 5 minutes between classes. I had no time for lunch, so I found out I had plenty of storage, so I was fine. But anyway, so let's go on and get started. Chapter 11 is Vectors and Geometry of Space. 11.5 is Lines and Planes in Space. And our objectives here are to write a set of parametric equations for a line in space, write a linear equation to represent a plane in space. Okay, so it's sort of a thing here. I already marked the present. So
I'm sorry.
No problem. Yeah. And we decided to go back and start at 11.5 rather than 11.6. Okay. All right. You probably don't have a book, or do you? Or
Not yet.
something like that. Just see
It's
if
coming in the mail.
Oh, okay. Do you have an ebook or something like that now?
I do not.
Okay. See if Dr. Bryant has this.
But
Want to use this, you can, but it's heavier than mine, I think.
that's a joke right there.
No. All right. So let's take I don't know if this is fair to do or not. Write a set of parametric equations for a line in space. So if you've got a line going through space somewhere, it'll be expressed by a set of parametric equations with one parameter to the first power to be a line. Write a linear equation to represent a plane in space. Okay? This is a set of parametric equations which are linear themselves, but you're basically identifying points with that. This is a linear equation to represent a plane in space, and we'll sketch the plane given by the linear equation and then find the distances between points, planes, and lines in space. Okay? Now, start with lines in space. Here's the figure, 1143 here. This, by the way, is on page 787 If you've got the same book I do, it's 11.5, 787. All right. Here's the line L here. Now this is the entire line L they're talking about here. Through a point P, x1, y1, z1, a point that you've got there, parallel to some other vector, ABC. Okay? Of course, that would be, and I'm not sure what text you may have used before, but this text, this author, typically uses parentheses to represent points, coordinates of a point, x coordinate. The angle brackets represent the components of a vector. Okay. Now, when you write that vector in standard position, which is from the origin, then those components are the same as the coordinates of the endpoint. Okay, so that is a point that would be ABC in parentheses, would be the endpoint there when it's written in standard notation. Okay, so, but when it's written as a vector as components, it's ABC, same ABC. Okay. The vector V is the direction vector for this line L, because once you have that vector V, then L has to be parallel to it. So that's going to be the direction vector for the line L. The A, B, and C are called the direction numbers. I like to think of them as direction components, but they like to call them direction numbers. So one way of describing this line L up here, okay, is to say that it consists of all the points Q, X, Y, Z. Now this is the variable X, Y, Z. These are specific points X1, Y1, and Z1. That's a single point. This is any old point that's on the line, okay? Has to be on the line, for which the vector PQ, P to Q, is parallel to V. Of course, this Q can be anywhere back this way or anywhere else up that way. It's just a variable point. The vector V, those are the components of the vector that this is parallel to. All right. Now, that means that the vector PQ, where P is the identified point, Q is a variable point somewhere out there, and this is a scalar multiple of V, that direction vector, and you can write PQ, because it's a scalar multiple of it, is some scalar times the vector V, where T is a scalar, any old real number. Okay? Now, let's go back to PQ here. And another way you can express this is the vector PQ is angle bracket x minus x1, comma, y minus y1, comma, z minus z1. That's how 2 points define a vector, where the initial point is this one, terminal point is that one. Okay? So this is an expression for PQ. Okay? X1, angle bracket, x1 minus x minus x1, y minus y1, z minus z1. But if that's also the scalar t times the vector v, that would be at, angle bracket, at, comma, bt, comma, ct. Okay? Which is, of course, tv. The two. No. Okay. So if those are equal, equating the corresponding components, you can obtain the parametric equations of the line, with this being your parameter, to be x equal x plus at, x1 plus at. So in other words, this is equal to that. X minus x1 is equal to at. So add x1 to both sides, you get x equal at plus x1, or x1 plus at. Y is equal to y1 plus bt, and z is equal to z1 plus ct. So that's your set of parametric equations that represents any line in place in space that is parallel to that vector C, B, A, B, and C. Components A, B, C. Passing through that point, X1, Y1, Z1. So this is all stuff you know on this side. Here's your variable X on this side, variable Y, variable Z. These are things given by the point. And the parameter you don't know, that's a variable too, in a sense. But the X1, Y1, and Z1 are what you like to know. So, now remember they call these the direction numbers. I like to think of them as direction components, but direction numbers is fine. Are all non-zero. Then you can eliminate the parameter t in the parametric equations and solve to obtain symmetric equations of the line. So, in other words, solve this for t, and you get x minus x1, which go back to what you had before divided by a. In fact, far easier getting that by going here, okay, and divide, this is t times v, so put this over t, that over t, and you get the vector ABC. Oh, I'm sorry, the other way. That's going backwards on. You're eliminating t, so divide by v here. I think that gives it to you. I guess better to use this one. Okay. X minus x1, what you had before, divided by a. Y minus y1 divided by b. Z minus z1 divided by z. You just do it, this a component at a time. Okay. This thing divided by a is equal to t. This thing divided by b is equal to t. This thing divided by c is equal to t. All those t's are the same t's, so that gives you your symmetric equations, they call these. Okay? And this is your variable, your point on the line, the variable that describes the line, and these are the direction numbers, direction components, whatever you want to call those, that is identified by your direction vector. That's what gives you the direction. That's what you decide on. So these are the individual parametric equations. This is the set of symmetric equations that define that same thing. The parameter eliminated. Okay. So here's example 1, which unfortunately they do. Well, I guess they do it all. Find the parametric and symmetric equations for the line L, this line L here, this light gray line L, that passes through the point 1. So on the x-axis you come up 1, the y-axis goes back 2, so there you are there, and then you go up 4. 1, negative 2, 4. Okay? Parallel to this vector here, which is 2, 4, minus 4. Okay? So there is the vector written in standard position, vector v, 2, 4, negative 4. Now notice I cut the endpoint the same way I did that point, because the components of this vector in standard form are the same as this endpoint. The coordinates would be the coordinates of the endpoint in that one. So get that. All right. So they've given you that. They said find the parametric equations. How would that go? Based on what we just did. Let me get my pen set up. And I was telling Bill before you came in, I left my reading glasses at home, so if I mess up a sign or something else, I'm not seeing well, so keep me straight here. So what are your parametric equations? X equal is what?
X minus x1.
Okay, either way you want to. You tell me what to do. Okay.
X equals 2.
Okay. Let me get back. Okay.
2 plus 4. 2 plus AT.
A T.
You know,
Okay.
2 in here would
Okay.
2 to A would be 2.
Okay, the A is 2. That's correct. Okay.
Let's do the same thing.
Okay. Okay. The A is 2, so there's your 2T. What goes at the front of that?
And then you got 2 minus 1.
Yeah, that'll be your 1. Yeah. Oh, okay. If you wrote it that way, it would be X minus 1 is equal to 2T. Yeah. That's what you were saying. Yeah. And then if you add the 1. Okay. So if you want to write them that way first?
Yeah, but
Top way? Or this way?
do we have to?
It doesn't matter. However you want to.
Okay, Y would be
Y would be equal to?
minus 2.
Yeah. Right. That's right.
Plus 4T.
4T. Perfect. And Z is equal to?
That's
4
plus minus 4T.
minus 4T. Perfect. So there are your parametric equations for the variables x, y, z. That's the parametric equations for that. What then would be your, what they call symmetric equations? And this is actually one set of equations, and basically just coming off of that. Right? X minus 1 over 2 equal y plus 2 over, whoa, come back. Okay, there we go. 4, and that's also equal to z minus 4 over negative 4. So you could write that as 4 minus z over 4 if you wanted to. There's lots of ways you could write it. All right, good. That looks good. Let's see if they got the same thing. Find the set of parametric equations for the line. Use the coordinates. X1 is 1, y1 is negative 2, z1 is 4. Direction numbers 2, 4, negative 4. And then your x is equal to 1 plus 2t. Let's see if they got that right. They did. And negative 2 plus 4t. They got that right. And 4 minus 4t. And they got that right. Okay. Now, ate lunch too fast. I've got hiccups, so sorry about that. Because A, B, and C are all non-zero, okay? Because you see, I meant to mention this back when we were doing it. Notice they said if the direction numbers A, B, and C are all non-zero, then you can do this. But if any one of them is 0, okay, you can't divide any of these expressions by 0. So maybe 2 of them would be okay, or 1, but yeah, they all have to be non-zero for that. All 3 of those work.
What do we do? Do we go that, I think we mentioned this sometime, go to that parallel thing, the plane is parallel to 0 or something like that?
Yeah, okay. If, just pick one of them. If your direction vector was 7, 0, minus 3, okay, that meant you're 7 on x, 0 on y, and minus 3 on z. That means you don't have a y component at all. So that vector, it doesn't, yeah, it disappears, exactly. So that would be something parallel to the xz plane. You're absolutely right. It would be something in the xz plane. Yeah. Right. Right. Exactly. Yeah. You nailed it. Okay. So that would then, that's what we got. Let's see what they got. They got x minus 1 over 2. Yes, is equal to y plus 2 over 4. Perfect. Well, is equal to z minus 4 over minus 4. That's what we got to. Perfect. Okay. So that was example 1. Bottom of 787. Yeah, all of 787. Okay. Any questions on that one? Here's how they did it. There's that part, and here's this part. Came up with the same thing we did. Okay. Now, it looks like to me they're skipping example 2. Now, I know that probably a lot of my blah, blah, blah last time left a lot to be desired, Josh. But on example 2, notice in that book, it says, see larsoncalculus.com for a interactive version of this type of example. I've got to get the book far enough away, but when it's small print, then it's too small to read. Okay. And that was the thing I was saying here. And if you look on the back cover here, you'll see this addressed here. Since you've got a book to look at it, there are 3 different electronic resources you can go to. The first is larsoncalculus.com, okay? And that's where these interactive exercises like number 2 is. You also find videos explaining the concepts of calculus, 3-dimensional graphs, videos with Bruce Edwards, who's the second author, and editable spreadsheets. I've never used a lot of that. But in addition to that, you have other sites you can go to, calcchat.com. When I make the first homework assignment, which I'll make at the end of the day, I'll say the odd number exercises are all worked out at calcchat.com, and then certain ones of them are also worked out in fuller detail, video solutions at calcview.com. So you have these three absolutely free websites. Anyone can go there. You don't have to be enrolled in the course anywhere else. There's no code necessary. I tell students your grandmother could go there and do this. You know, so even if you don't actually have a book, you can get a lot of the examples. Not a lot. Every now and then the example will be there. The odd number exercises will be there, and some odd number exercises. Okay, so you can do a lot without actually having the book. Okay. Now, to me, the problem with that is, if I think of myself as a student, those are all things worked out for you. You just got to turn it off and just get what the problem is, let that go aside, work it out yourself, and then check and see if you got it right.
Otherwise, you don't learn anything.
Yeah, it's exactly. It's all past it. Oh, yeah, I see how they did that. I see how, but you don't actually do it yourself.
Where do I start?
Yeah, exactly. Right. So that's where it's an advantage to actually have the book.
I've messed up before.
Yeah, okay. We've been there. Huh? Okay, so let's go to example 2, which is also located at larsoncalculus.com. I've got standby. Let me back up so I can find a place to write. I guess that's going to be the one and only place to write. Okay. Okay. Find the set of parametric equations of the line that passes through the points -2, 1, 0, I think it is, and 1, 3, 5.
Yes,
Okay. Now this time they just give us a 2 points without giving us a vector. Okay. It says find the set of parametric equations of the line that passes through those 2 points. How in the world are we going to do that if they don't give us the direction vector?
create a vector of those 2 points.
Yes, these 2 points will give them to you. So how do you get that? Let's just go on and name it V. Now I can't write bold like the book does, so my vectors have little arrows over them. And what would that vector, one representation of that vector be?
1 minus a minus 2.
Okay. Okay, that would be 3, comma.
3 minus 1 is 2.
Got it.
5 minus
5. Good. All right. There is our direction vector then. You see how we got it? No. Yeah. All right. Okay. Given any 2 points.
Subtract it.
Yeah, subtract. And build it the way I like to do it. Bigger number minus smaller number. You know, at least the majority of times, all 3 of these, that was the case. So there's your direction vector. Okay? Now, it said, at this point, it's pretty easy, I guess, I would hope anyway, to find the, okay, I'm sorry. I'm having trouble reading. Okay. Find the set of parametric equations. So we got our direction vector. What would be the set of parametric equations? What you have to do now?
X1.
X.
X is equal to, let's go minus 2.
Okay. Now, what Bill has done, he's chosen one of these to be the point. It doesn't matter which one. It really doesn't. He chose the first one to be the given point, so minus 2 plus
Direction will be t.
Second?
Plus t.
3. The parameter, t.
It's just 3t. Is it 3t?
Yeah, that's a 3. It's an ugly 3, but it's a 3.
Just t.
Okay, that was a 3. Because it was, remember, it was 1 minus a minus 2. That gave us a 3.
Yeah, that's the 3.
So the direction number, or the,
yeah, I was looking back at before direction number.
Yeah.
Okay, 2t, b would be y would be 4t, and c would be minus z would be 4t.
Okay, now this is the previous problem. This is the problem we're dealing with. Right, okay. Yeah, we're dealing with this one now.
Okay.
This is a new vector. I just needed room to write. They didn't have it on the slide stuff. Okay?
I'm sorry.
Yeah, no problem. So you pick either one of these you want. It doesn't matter which one. You could pick this one or that. Either one. It doesn't matter. I thought since you started with minus 2, we were going to start there, but we could go 1. Okay. Plus 3t. Okay? But if we... Yeah, exactly. Exactly. So the next would be y is equal to 1 plus 2t. And z is equal to 5t. Right? Yeah, okay. 0 plus 5t. Okay. Now I said you could go either one. Is those the same equations as x equal 1 plus 3t, y is equal to 3 plus 2t, and z is equal to 5 plus 5t. Okay? Doesn't quite seem fair for that to be true, but is it? Well, if your t is equal to minus 1, let me see if I'm saying that right. For t is equal to 0 here, that would give you negative 2. T was minus 1 here, that would give you minus 2. Well, this would be a 1, this would be a 1. If this was a minus 1 here. If this was, this would be a 0, and this would be, so every point would match up. Just 2 different sets of parametric equations that give you exactly the same points, just for different values of t. Okay. So yeah, they are the same.
So t is going to be the.
Yeah. I probably should have let this be an S rather than a T. It's not the same T. So,
yes. Okay.
Yeah. Okay. Let's do it that way. Or T1 and T2 or something like that. I probably. Yeah. for a different parameter, S, or any parameter you wanted to have. Probably shouldn't have used T. But they do describe exactly the same line. Just a different value of it. When this T is 0, this S is -1. When this S is 0, this T is +1. Okay? And so they'll give you you will find the parameter for everyone that produces a certain point here. There will be a parameter that produces exactly that point, same point here.
But I see now when they do the solution book, it's going to be a little bit different from the way we started, because they probably won't use the terminal point.
Right, exactly. But every point in between is still there. Right. Yeah. Okay. So let's see what they came up with. I think they did it the same way Bill started us. X equal -2 plus 3t, y is equal to 1 plus 2t, and z is equal to 5t. Okay. And the remark they give here, if I can read it, as t varies over all real numbers, the parametric equations in this determine the points x, y, z on the line. In particular, note that t equals 0 and t equal 1 give the original points. That's what we just said, -2, 1, 0, and 1, 3, 5. Okay. All right, so let's move from lines in space to planes in space. Okay, so this time we're going to consider a plane that contains the point P, x1, y1, z1, just like we had before. There's the point. Now that point is not just in a line, it's in a plane. Okay? Now, you need to know something else about the plane, okay? Just like before we had to know the line was parallel to some given vector v, this time we pick a non-zero normal vector to that plane, okay? Now, normal vector to the plane, and we're going to pick the same values of it, a, b, c, okay? Some vector that's normal to that plane. And that's going to be this vector here that's perpendicular to the plane, and that normal vector has components a, b, c. And that plane consists of all points q for which the vector pq is perpendicular to do. So whatever q you have in the plane, it's always going to be perpendicular to the normal plane. Okay? Every vector pq has to be perpendicular to that. That's what makes it a normal vector. So, if they're orthogonal to each other, that means the dot product is 0. So n, which is ABC, dotted with PQ, which is, again, x minus x1, comma, y minus y1, comma, z minus z1, that has to be 0. Because every q in the plane has to be orthogonal to its normal vector. So this gives us another set of equations. A, the dot products, remember how you do those? First component times first component plus second component times second component plus third component times third component is equal to 0. You get a scalar equation here when you dot two vectors. Okay? So this would be a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. Perpendicular. Third equation of the plane is said to be in standard form. What in the world does it mean, third equation? I guess this one. 1, 2, 3. I guess that's the standard form of a plane given a point in the plane, one point in the plane, and the normal vector to the plane. This is the standard form of that plane.
Well, we're going back to the equivalent, like we was in algebra. We had ax plus by. Is that equivalent? You remember that? Because we got the slope and the out of that. What is
Yeah.
of the intersection.
Yeah.
Out of AX plus BY, as you can see.
Yeah.
Is that equivalent?
Let's see. Yeah, each one of these looks like an equation of a line, kind of, but they're only in the plane. With the projection of this onto the XY, I don't know. It's a good way to think of it, but whether there's a direct connection there, I'm not sure. Sure seems like a good way to think of it. But basically, whereas before that vector was called the direction vector when you're drawing a line parallel to it, now basically your direction vector is the normal to the plane. If you're doing that, gives you your direction components, which seems bizarre because that's perpendicular, but because of the dot product, that is exactly what it turns out to be. Now notice these aren't equal to each other. This is one equation, a linear equation, by the way, that gives you the standard form of a plane. Okay? Now, sort of the thing that makes maybe the tie that Bill was talking about, because it's a plane, everything, you can't have any curves in this plane. Planes are, in a sense, linear in every dimension. So, in that sense, maybe that sort of ties with what you were saying, perhaps. I don't know. I may have missed something there. But that's your standard form of an equation for a plane. All the variables are first power. Okay, so here's theorem 1112. Okay, the plane containing some arbitrary point x1, y1, z1. All you need is one point and know the normal vector. The normal vector happens to be ABC, then that plane can be represented by the standard form of the equation of the plane by A times x minus x1 plus B times y minus y1 plus C times Z minus Z1 equals 0. Comes directly from the orthogonality of the normal vector to every line in the plane. By regrouping those terms, just sort of like we did before, you can obtain the general form, that's the standard equation, the general form. So you multiply this, and maybe this is what Bill will talk about. A times x is ax plus some constant. A times x1. That's a constant, that's a constant. Plus by minus this constant, okay? Plus z times this constant is equal to 0. We'll add those three constants together, make it a constant b. So this is another way you can write the general form of the equation of the plane. They call this the standard form. This way you see what that initial point was. In this form, you don't see that, but you still see those, just for lack of a better word, the direction components, okay, A, B, and C. This time it's for the normal, last time it was the line parallel to it, okay? You just lose the x1, y1, z1 in this form. Actually, personally, I like to move this to the other side and have ax plus by plus cc is equal to some number. Yeah. Now, given the general form, that's this one, of the equation of a plane, it's easy to find the normal vector to the plane. There it is, A, B, C, okay? Anytime you have an equation of a plane, take the coefficients of the x, y, and z, that's your normal vector, okay? Simply use the coefficients of x, y, and z and write that as your normal vector. A piece of cake, okay? All right, so let's do example 3. Find the general equation, not the standard, the general equation of the plane containing those 3 points. Whoa here. This isn't what we were doing, is it? That kind of is. What are we missing? the normal vector. If we knew the normal vector, it'd be really easy to write. We don't know it though, do we? Okay, so how are we going to get that normal vector?
Cross product.
Okay, good, good. What does the cross product tell us?
I'm not sure what it tells you how to do it. But it tells you it was orthogonal.
Yes.
Oh, yeah.
Yeah, the cross product is always orthogonal to the two vectors making them up. So none of these had better be collinear. If so, you can't get a cross product, okay, from that. But let's do it. Good idea. So what's the cross of 2, 1, 1 cross with, wait. I'm not doing this right. Start back. Goodness gracious, it's hard to see. Okay. You tell me what we should be crossing. I shouldn't be telling you.
You pick any two, right?
Pick any two and what you do with them.
I'll say IJK at the top, and then 2, 1, 1, and then 1, 4, 1.
Okay. That's what I was starting to do, but these are not vectors. These are points.
You do the same thing you just did where
Create a vector.
Second?
Create a vector.
Yes, create the vector. And what would be, give me a vector. Give me one of these vectors you're going to create. Let me get my pen back, okay?
do 2 plus 2.
Second?
2 plus 2.
Where do you get that?
First and the last one.
Oh, first and the last, okay. Oh, I see. You're subtracting this one from that one. So that'd be 2 plus 2, comma, 1, comma, second?
3.
Okay.
4 minus 1.
Okay. Go one way or the other, but don't question mark. Yeah.
5. Do 1 minus -3.
-3. Good. Okay.
I don't write it down.
Yes, exactly. So that's going to be 4, 1, minus 3. There's a vector that you get by having, let's see, that be your initial point and this be your terminal point, right? 2 minus a minus 2 is 4, 1 minus a 0 is 1, and 1 minus 4 is -3. Okay, there's a vector. I need another one. It's what? First two, okay. And what will that give us? 1.
3
minus 3 and 0. Okay. All right. Now we have two vectors, and now we do what Bill was suggesting. I, J, K. I don't know if this is how you did your cross products. Set up a determinant.
Yes, and then I cover 1.
Yes, okay. I, J, K, and then write, doesn't matter which order we do, 1, -3, 0, and, yeah. 4, 1, -3. I did do that right? No. Oh yeah, I crossed up the order. Okay. It doesn't matter the order. And then repeat the first two. I, 1, 4, and J, -3, 1. I always do cross products like this if they're three-dimensional. Okay? Then do your down diagonals here, and what does that give you? 9I. Second? 0J.
1.
Plus K. Okay.
I've never seen it with IJK and then
IJ.
another IJ.
Okay.
Just always did it 2 separate ones.
and then, you know, crisscross, yeah, and do plus and minus and stuff.
This does seem easier though.
It is pretty easy, except you just have to remember when you do your up diagonals, you have to do the minus of them. Because your up diagonals are negative when you're doing determinants. So this would be,
-12.
except you do the minus of that, which is
Plus.
plus 12k. Keep the letters with it, okay? This would be 0i, and this would be
3J.
plus 3j. Now combine those together and you get 9i plus 3j plus 13k, if I did it right. Okay? That should be your normal vector. Okay? Because it's perpendicular to both sets of vectors that you get from combining any two of those together. Okay? You could have done any one of those with the second and third vector. You can go back and try that if you want to. Okay. Now what do we do with that? General equation. Okay. How do we do that?
9x
9x plus
3y
right.
plus 13z. Let's see what we add up here.
And what?
You got to add up something. D.
Yeah, now what? So something you got to add up. That's where the question comes. We got those, but finding that D.
Other vectors up there.
Yeah. All right.
Let's say 9 times.
Okay. Now, remember, we don't use the vector. We use the pointers. Yeah. Right.
So 9 times 2, that's 18 plus.
Okay. Oh, okay. Okay. So you're doing.
The first point.
Now, I'm a bit slower than you are, I think. So I'm going to do 9 times x minus, you said, 2
Yeah.
plus 3 times y minus 1. Is that the one you're using? Is that right?
1.
Right. Plus 13 times z minus 1 is equal to 0. Okay. That comes from your cross product. Okay. And so, yeah, what you do here, you got your 9x plus 3y plus 13z, and then you got minus 18, minus 3, minus 13, minus 31, minus 34. I did it fast in my head. I'm not sure I did it right, especially since I can't read. I'm really getting dizzy even trying. Let's see. Yep, I think that's what they got. Okay. Did y'all get it? Okay. Take your time.
Well, we got it now.
Okay.
It's up there. Well, that's what I was doing.
Right, exactly. I figured you were, but I just couldn't keep up with you, so I had to write it down. If I was trying to store it up here, that gets lost somewhere, you know. The old gray cells ain't what they used to be. Now, frankly, I like to say 9x plus 3y plus 3z, 13z is equal to 34. Somehow that just looks a lot better to me than minus and equals 0, but that's just me. Okay. This was, by the way, your standard form, or something pretty close to it, if we had multiplied through. This is what they call the general form, and that's what they were asking for, general equation. Okay. Now, they have a little remark here, if I can read it. I got to get the book far enough away. and enough light to see it. In example 3, check to see that each of the 3 original points satisfies this equation. So yeah, pretty good check here, okay? So let's see if 9 times 2, we already know this one, is 18 plus 3 plus 13. That better be 34, and it is, right? Let's do the other 2. 9 plus 12 plus 13. 9 plus 12 plus 13. That's 25, and 9 is 34. Yes, that one works. Let's see that last one, okay? Minus 18. Is that right? No, I'm sorry. Yeah, no, that's right. Minus 18 plus 13 times 4. Not going to do that one in my head. That's 42? No, 52. Yeah. How many cards on the deck? Right, okay. That's 52 minus, what was it, 18? Yeah, 52 minus 18. Sure enough, is 34. Okay. See what we're doing? Okay.
I do. The way we learned it over the summer was we completed the square and everything.
Yeah.
And
Wasn't that a joy?
and then solved. Oh yeah.
I can tell.
This is a lot easier.
Yeah.
Just plug in a number. It's
Yeah.
already there.
Yeah.
Very
So,
nice.
there may be circumstances where you do need to do that. If you were given an equation first, then yeah, that's what you have to do to get back to this. But this, they just gave you the point, so this one's really easy. Yeah. Okay. We might get to the hard part in a minute. We'll see. Okay. Now, that was example. Oh, that was how we did it. Let's see how they did it, if they did it any differently. Is it all right to erase? Okay. Let's see what they did. To apply Theorem 1112, you need a point in the plane. You got 3 of them. Choose any one. And a vector that's normal to the plane. That's where the rub comes. So how do you get that? There are 3 choices for the point, but no normal vector. Okay, so what do? We pick any 2 vectors from those 3 points. To obtain a normal vector, you use the cross product of any 2 vectors, u and v, extending, now they said, both from 2, 1, 1. You didn't have to choose that. It's actually the one I think we did choose, if I'm not mistaken. I think I've already erased it, yeah. But anyway, it doesn't matter. Any 2 vectors from any one of the other 2, from one of the other 2 points, okay? And they did this one, and that was the vector, not sure their picture is really helping me any.
They did the same as us.
They did the same
Opposite,
too. Yeah, I think they did do the same too. Okay.
Opposite order.
Yeah, he picked the last 2 and we picked the
Yeah, first.
two.
Right. Okay.
Last 2.
No, you picked the first and the last, and or somebody picked first and last. The other picked the first 2. Yeah. Okay, that's it. Yeah, you're right. Okay, and we got that. -1, 3, 0. I think we did it the other way. We did 1, -3, 0. It's all right. It doesn't matter. Doesn't matter. And the other was, I think we did 4, 1, -3.
Yes.
Okay? It doesn't matter. Okay? Those are just opposites of each other. And then do the cross product of those. And you did your u is the normal vector would be u cross v. And they didn't show how they did it. They just came out with 9, 3, 13. 9i plus 33j, which is exactly what we got. Okay? And that's your ABC. Simple as ABC. Okay, never mind. Using those direction numbers for n and the point x1, y1, z1, Did we use 211? I think we did. So we did do a lot of the same thing that they did. You can determine the equation of the plane, standard form, to be 9x minus 18 plus 3y minus 3 plus 13y minus 13, and add those together, you get, well, there they did it for us. I don't see they regrouped, they just distributed, okay, and got those. And then when you regroup, oh, I see, then you get that. 9x plus 3y plus 13 is equal, or minus 34 is equal to 0. Standard form was up there, general form down there. All right, pretty much just like we did. A little bit of backward things the book did, but I liked our way better. Two distinct planes in 3 space either are parallel or they intersect in the line. Two distinct planes either have to be parallel, never intersecting, or they're going to intersect, but if they intersect, it's going to be a line. Okay? For two planes that intersect, you can determine the angle, and it's always an acute angle between 0 and pi halves. Between them, standing up, I hate sitting too long. Okay? You can determine the angle, the acute angle between them, from the angle between their normal vectors. Okay? So, if you have two distinct planes, if you know their formulas, you know the normal vectors. The A, B, and C are the coefficients of x, y, and 2.
We don't have that yet, do we?
Say again?
We don't have that yet, do we?
Yeah, we just did. Okay. We haven't been given it to us, but this, that normal vector.
We just did.
Yeah, those are the components of your normal vector. Okay? So if they give them to you, you already know what they are. Okay? Now, then the angle between the two vectors is also the angle between the the two planes will be the angle between the normal vectors. Well, how do we get that? Okay? Specifically, if vectors n1 and n2 are normal to the two intersecting planes, then the angle theta between the normal vectors is equal to the angle between the two planes. And here's, if you remember, the alternate definition of a dot product. Let's go back here. Remember, one definition for dot product, if you have A1, A2, A3 dotted with, and I'm sorry, that's not at all what I wanted to write. Okay. A1, B1, C1 dotted with another one, A2, B2, C2. Then we just said this was A1, A2 plus B1, B2 plus C1, C2. Yes, that's one definition for a dot product. You multiply the corresponding things, add them up. Okay? But remember, there was another definition. The dot product, let's call it U1 dot U2. I'm writing faster than I'm thinking or something, and I don't think very well at all. Okay, dot U2 is equal to the magnitude of U1 times the magnitude of U2 times the cosine of the angle in between. And since that's what we're looking for, I was going to say theta 1, but we don't need that. It's just cosine of theta. So that then gives us the dot product of the two vectors, U1, which you get just like this, U1 dot U2 divided by the magnitude of U1 times the magnitude of U2. That's equal to the cosine of the angle in between, or the angle in between is the inverse cosine of that. Let me just do it that way. Inverse cosine of that. Make sense? Okay. So, that's what they got here. Oh! You need to put absolute values there. Because since you're dealing with only acute angles, this needs to be positive. And there is a chance that the dot product of those could be negative, depends on which orders you did or whatever. So you want the absolute value of that. Because these two are always positive. The magnitudes are always positive. So that's going to be positive. You just need the numerator and positive too. So you do need the absolute value bars there. Consequently, two planes with normal vectors N1 and N2 are perpendicular when their dot products are, the dot product is zero. Dot product, normal vectors is zero. They're parallel when N1 is just a scalar multiple of N2. In other words, they're scalar. They're along the same line. Okay. Now, so if that dot product is zero, the only way cosine of theta can be zero is if it's 90 degrees, right? Or pi halves. So that means they're perpendicular planes. The only way they're parallel, then the dot product would be exactly the product of these two. So it's going to be 1. That means the angle. The only way that's going to happen is they are just scalar multiples of each other. Okay, got to find where I am now. I think this is where I turned the page. I'm having trouble seeing. Oh, they're skipping example 4. Shame on them. So let's go back, find some white space, and we'll do example 4. Find the angle between two planes. Here's the first plane. X minus 2y plus z is equal to 0. Interesting. And 2x plus 3y minus 2z, I can't read, is equal to 0. Now, okay, find the angle between those two planes. Can you tell me anything about those two planes just looking at their equations? Do they, we know they have a line in common, do they have a point in common? 0, 0, 0 goes through both of those. So these planes intersect the origin somewhere. However they do it, they're going through the origin, okay? In other words, we're missing our D on both of them, okay? Without the D there, they got to be going through the origin. Okay. I found it interesting they did that, okay? Then, okay, so first let's find the angle. So how are we going to find the angle? What do we need to find first? Okay, let's call this one 1 and this one 2. Why not, okay? So what is your N1? 1. Negative 2? 1. That was easy, wasn't it? What is your N2? 2. 3. Negative 2. Now, okay, I think these are going to have one. Okay, so what do we do next? Okay, you can do that anytime. You got to do it sometime. So let's do magnitude of N1, would be the square root of 1 plus 4 plus 1. That's going to be square root of 6, right? Okay, what's the magnitude of N2? And that's going to be 25? No, I can't add. Okay. 8 plus 9 is 17, right? I can't add. Okay, 17. All right. So we got the two magnitudes. What's the other thing we got to do? Dot product. So what's N1 dot N2? 2 minus 6 minus 2, which is equal to negative 6, but we want the absolute value, so we're going to use 6. So the cosine of the angle in between those two is going to be the absolute value of this, which is 6, over root 6, root 17. What a lovely number. Okay. Pull out your handy-dandy calculators, see what that is, and then do an inverse cosine of it. But neither one of you brought a handy-dandy calculator, did you?
I got 2.
Oh, you do. Let Bill use one. First, I want to convince myself that's going to be a number less than 1. It's got to be, right? Absolutely has to be, because cosine is never greater than 1. Okay? Well, since square root of 17 is greater than square root of 6, if this was square root of 6 times square root of 6, that would have been 6. So this is going to be greater, so the denominator is greater than the numerator, it's going to be less than 1. Okay, that's the cosine?
Oh, that's the...
oh, no. Oh, that's the what? That's the
cosine negative 1.
oh, that's the inverse cosine.
Yeah, inverse cosine.
Okay, and that's in radians, I take it then, all right?
Yes.
Okay. All right. Let's see what they give their answers in. Okay, say what you got again?
0.78.
Whoa. Oh, okay. I've got to find where they gave their final answer. I don't see where they gave their final answer.
I did it wrong. I apologize. I put 12 instead of 17.
Oh, yeah, it's my lousy writing, probably. Okay.
It's not much different, though.
Okay, and do it in degrees, because they give their answer in degrees. Waking up people at home. Okay.
You have no earthly idea how to change it.
Oh, what? Wait, what?
Not on that one, I don't. Do on this one. I'm going to trace it.
Okay. Oh, I see. You've already taken the story. Yeah, that's the right answer there. And then how to get an inverse cosine of it? Oh, to get it to degrees.
Yes, get it to degrees.
Oh, I
know
see. So this is too fine a print. I can't hold it far enough way to read it, or if I do it, it's too small to read. Yeah, I'd have to. Yeah, that's all right.
You got some, what?
Yeah. What number did you get in radians? 0.93 what? 46. Okay. Now, to get that to degrees, this is radians, there are 180 degrees for every pi radians. Okay, right?
Right.
Okay, so multiply that number by 180 and divide by pi.
53.54.
That's, I think, exactly what the book got. They got 0.55. 53.
Oh, yeah, it rounds up to it.
53.55 degrees, yeah. So, even on that one, you can come up with it fairly easy. Okay. Now, that was the first part, if I can see where to go here. This is making me dizzy. Okay. Find the angle. We did that. Okay. Then find the parametric equations of their line of intersection, okay, between those two planes. The parametric equations of the line of intersection. Okay. Okay. Now, what has to be true here is that these two equations have to be solved simultaneously. I mean, they have to produce the same result, because every point that's on that line has to be on both of these equations. So what we're going to do is solve these two equations simultaneously with each other. Okay? Now, I'm probably going to need to erase some to have room to do this. Is it all right for me to erase? I don't think I need this information anymore. You've got it though, right? 53.55 degrees? Okay, so I don't think I need the normal vectors anymore, but if so, they're easy to get. We can get the magnitudes very easily too. I'll just look down at the page, and I don't think we need the dot product again, so we'll get rid of that. And we've already calculated the angle, so I'll get rid of that as well. So going back to the original, we might need that angle, but I'll ask y'all what it is because you have it written down. I don't think I'll need it, but let's see. Okay, so what we know is that simultaneously x minus 2y plus z is equal to 0, and 2x minus 3y minus 2z is equal to 0. Okay? Now, how they recommend you do this, and it makes sort of sense, you're not going to be able to miss everything, but at least you can eliminate one variable. Okay? You only got two equations, three unknowns. You're not going to get a unique answer, but you can eliminate one. Now, the easiest one to me to eliminate would be z, because they have opposite signs and it's a simple multiple. So let's multiply the top equation by 2, and the bottom equation we'll leave alone. So you have 2x minus 4y, don't make mistakes, okay, plus 2z, I can't write, okay, plus 2z is equal to 0, and 2x minus 3y minus 2z is equal to 0. Add those two together, you lose your z's, and you get 4x minus 7y is equal to 0. Solve for one of them, like x. 4x is equal to 7y. Divide by 4, and you get x equal 7/4 y. Okay? Now, Goodness gracious, I can hardly breathe. Now, okay. They didn't do it the same way I did, but it's okay. Let's plug that into either one of the original equations. I don't think it comes out the same way. Just, no, not quite. Okay. Not even close. Okay. Is any one of these any better than the other? I would do the first one. Okay? No. Let me see. It doesn't matter. So we'll do 7/4 y minus 2y plus z is equal to 0. Now 2y would be 8/4, right? Y. 2 is 8/4. So that would be minus 1/4 y plus z is equal to 0. Okay? Goodness gracious, I'm having trouble reading this. So z is equal to minus 1/4 y. Okay? So it looks like an easy thing to do was let y equal your t, your parameter. Okay? So you have x equals 7/4 t, y is equal to t, and z is equal to minus 1/4 t. Okay? Now, they didn't like the fractional forms, so let's multiply each of those equations by 4. And that'd be 4x, let's see, does that work? Nah. Let's multiply just the y is equal to 4t. Let's do that one, okay? That will be better. If you multiply all of those by 4, you have x is equal to 7t, y is equal to 4t, and z is equal to minus t. Goodness gracious. Okay, that's not quite what they got. But let's see if we're way off. If you subtract 6t from each of one that I did, that would give you x equal t, y is equal to minus 2t, and z is equal to minus Okay? That's closer to what they... No, it isn't. Goodness gracious, I've made an error somewhere here. And probably because I'm not reading right. I'm awfully close, but not quite. Yeah, sorry about that.
When you multiply by 2,
Okay. Let's see. I may have just even written down something wrong. Let me make sure I wrote it right. Goodness, my eyes are driving me nuts here.
It was a negative 3y. It's supposed to be positive 3y.
Okay. Where is... Oh, is it?
Yes.
You're right. That's... Yeah, there's it is, right there. That's... Yeah. So no wonder everything's screwed up. Okay, so sorry. Sorry about that, team. I think everything's going to go away. So, okay. We were so close, but not quite. All right, sorry about that. I'm glad y'all have better eyes than I do, which isn't saying much. What's that?
I have to do that quite often.
Okay, so when you add these together, you get 4x minus y is equal to 0, so y is equal to 4x. Okay? All right, that's looking better. Plugging that back in, to, say, the first equation there. Yeah, why not? That would be x minus 8x plus z is equal to 0. That would give us negative 7x plus z is equal to 0. That's a z. And that would be z is equal to 7x. So let x equal t, y is equal to 4t, and z is equal to 7t. Yes, 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 that's exactly what they got. Okay, I think we did it slightly differently, but it still works out okay. Now, and again, they're passing through the origin, so that's the point you can use, and that's why there is no x1, y1, z0, x1, y1, z1 here, because we're letting that be 0. Okay, you knew it had to pass through the origin.
Question.
Yes.
On your election of T, why did you pick that T? Did you just arbitrarily just...
Okay, I saw that y was equal to 4x and z is equal to 7x, right? So since we got to come up with a parameter, let's let x equal the parameter, because then you get z is equal to 7 times that parameter and y is equal to 4 times the parameter. Nice round numbers, you know, whole numbers. That's why I did it. I was lazy.
Is that because the 0, 0, 0?
Well, the reason 0, 0, 0 is that you don't have anything added to this.
Yeah, but I'm saying, is that the reason why you picked the T?
No, I just let these, from these two things that we got, that's when we eliminated z. Then when we plugged this in for y, then you eliminated your y basically and got x's and z's. And then you came out with these two equations, and you need a parameter, and that was just the sort of the logical one. Let x equal t, and then z will be in terms of t, y will be in terms of t. Yeah, it was just to make it easy. You could have chosen any one of them, but if you'd chosen z to be your t, then x would have been t over 7, and then you'd have to do all sorts of other things there, and it would just been messy. And I'm just too lazy to do messy. So it was the easiest thing to round to. Okay. Now, if you remember, okay, what we're looking for is a line, and the coefficients of your parameters are your direction numbers. So the that's what they call them. I like to call them direction components, but they call them direction numbers. And second, 147. Yeah, yeah. So what was the question? I've forgotten it. Find the parametric. Oh, we found them. Those are the parametric equations of the line of intersection between these two planes. Okay. Now, the other way you could have done this, and this is the way I was starting to, but the book wasn't heading that direction, so I tried to go the direction the book did, is once you had the two normal vectors, which we had just gotten before, that you could get off the original things, just do a cross product for them, and the cross product of those two normal vectors has to be in the same direction of the line of intersection. Okay? I don't know if that's completely obvious. Says note that the direction vectors and direction numbers in example 4 can be obtained from the cross product of the two normal vectors. Because if that's a normal vector to this plane, and this is a normal vector for that plane, the line that is the intersection between has to be normal to this plane and normal to that plane. So yeah, that would be you find that normal vector, the vector that's perpendicular to both of those, same vector, it has to have the same direction numbers, direction components. So that was the other way you could have done it. Frankly, I think I'd found that way a little easier than the way we just did. So let's just do it and see. Where these are two normal. Yeah, these are the two normal. Yeah, the two normal vectors. So let's do that. I, J, K, I, J. I'd do it the lazy way. Okay? 1, -2, 1, 1, -2, and 2, 3, -2, 2, 3. Okay? Down vectors would be for I. Down diagonal would be plus 2j. Down diagonal vector plus 3k. Up diagonal, but the opposite of that would be a plus 4k. Up diagonal here would be a minus 3i. And up diagonal here would be a plus 2j. Add those together, you get I plus 4j plus 7k. There's your 1, 4, 7. 1, 4, 7. So you can get them that way. I found that a little easier than all the things we did there. Huh?
Way easier.
Way easier, right.
Way easier. I'm going to have to go back and look at this.
Okay. You the one that wanted it. Okay.
Yeah, that's what's the problem.
Exactly. All right, so that was example 4. So we've done lines in space, dealt with planes in space. Now we don't want to, sketching planes in space.
Before you have a question,
Yeah.
may I have a question?
Oh, sure.
Okay, normally we look at the planes as the walls here, like
Right.
this. Now, can we have a wall that they translate, the planes translate, like put the whole wall,
Right.
like the z-axis here,
Right.
flip it over here,
Right.
and have the y this way, and then
Yeah.
the x. Do we do that in this type setup?
Let me
Or is that
think.
way beyond the scope of this?
I don't think they have that in this section for sure, but I'm trying to think which section they might have it. I'm having so much trouble reading. Okay. Thought maybe it was chapter 10, but I don't see it there.
Well, do we just have to go back and read where planes are shifted?
Yeah. I don't see it here, but I know I've done it. I can't remember if it was in a calculus class or if it was in physics. But you have to, twist things around in physics a lot, like if you're dealing with an inclined plane, you want that to be your axis like this, not like this, or that. So you do that kind of thing, but I'm trying to think if we've done it in space where you might be twisting all three of them. That does become sort of a real big pain in the neck, I think. And I bet you use dot products and cross products to do it. I'm not quite wrapping my head around exactly what would be an easy way to do that right now. But I bet you that would involve them. Now, there's other things that are involved too. And I think they're the Jacobians, but if they're not Jacobians, they may be Wronskians. I don't think they're Wronskians. There's some sort of a procedure that you use to do that is relatively straightforward to do, but it's not straightforward to remember. You almost have to go look it up, and then when you have it, sort of plug and chug or something. It's been so long since I've done that, I don't recall the procedure for doing it. But I bet you that's pretty closely related to what we're doing here. I just can't tell how far a distant cousin it is. All right, so let's go to sketching planes in space. Now, y'all have to keep up with my time for me. I don't even have my watch out. Are we over?
No, it's right at it.
Really? Okay, yeah. Okay, sorry about that. We will pick up with sketching planes in space next time, okay? And one time or another, I had my pencil out here, but I must have put it back, yeah. So we'll start out with sketching planes in space. I'm sort of glad you asked to do this because it's been a long time. In fact, I'm trying to remember in this book, I don't think I ever got this far in chapter 11. So I'm glad you're asking this. This is good. So we'll pick up there. Now, let me give you your homework exercises. Let me get something to mark my place here. Okay. We came close to finishing the section. Do number 5. Do any of the odds 7 through 11. Oh, and by the way, number 5 you can find at calcchat.com. Any of the odds 7 through 11, they're all at calcchat.com. 9 is at calcview.com. Do 13 or 15, they're both at calcchat. 15's at calcview. Any of the odds 17 to 23, they're all at calcchat. 25 or 27 are at calcchat. 29 or 31 are at calcchat. 33 or 35 are at calcchat. 37's at calcchat. Any of the odds 39 to 43 are all at calcchat. 39's at calcview. Any of the odds 45 to 55 are all at calcchat, with 47 at calcview. 57 or 59 are at calcchat. 61 or 63 is at calcchat. I think 65 and 67 are both at calcchat. 65 is at calcview. And I think you can do 69 to 73 with what we've done so far, and they're at calcchat. Stop there, though, because the rest of them are sketching, or sketchy, I don't know, one or the other. So we'll pick up the rest of those next time. Okay, good deal. So we'll pick up with sketching planes in space. Thanks for stopping me.